Today I am going to discuss the relationship between the primal problem and dual problem, which are in the form of duality theorems. The first theorem which I am going to discuss is weak duality theorem. Let us consider the primal and dual pair as our primal problem is maximize objective function C transpose X subject to the conditions Ax less than equal to B with non-activity restrictions, that is X greater than equal to 0. Here X is n-dimensional vector, C is an n-dimensional vector, B is m-dimensional vector and A is coefficient matrix of order n cross n. Now, dual of this primal problem is to minimize objective function B transpose W subject to the conditions A transpose W greater than equal to C with non-activity restrictions, that is W greater than equal to 0. Now, here W are dual variables. How to form this dual? This I have earlier discussed in my first video. Now I am going to state weak duality theorem. Say the statement of weak duality theorem is let X be feasible solution for the primal problem and W be feasible solution for the dual problem. Then the objective function value of maximization problem can't be exceed the objective function value of minimization problem, that is C transpose X is always less than equal to B transpose W. The important thing is that this theorem is corresponding to feasible solution of both the problems. That corresponding to feasible solution of both the problems, maximum value of problem can't be exceed minimum value of problem. Proof of this theorem is since X is feasible solution for primal problem. Now we recall what is feasible solution. Feasible solution is those solution which satisfies the constraints as well as non-activity restriction. Therefore, since X is feasible solution for primal problem, therefore Ax less than equal to B along with X greater than equal to 0. This is say equation number 1. Also given that W is feasible solution for dual problem. As W is feasible solution for dual problem, therefore A transpose W greater than equal to C along with W greater than equal to 0. Say this is our equation number 2. Now look at the objective. Our objective is to prove C transpose X is less than equal to B transpose W. Here we wanted B transpose. Where is B in our picture? B is here. Ax less than equal to B. Therefore, we started from here, that from equation number 1 we get Ax less than equal to B. Now we want transpose on B, therefore I apply transpose on both sides. Ax whole transpose less than equal to B transpose. Apply reversal law of transpose. This becomes X transpose A transpose less than equal to B transpose. Now we want W with B transpose. Therefore, I multiply with W on right hand side of above inequality. One thing is important there, that as matrix multiplication may or may not be commutative, therefore we multiply with W either on left hand side or on right hand side. That is, there is concept of pre-multiplying or post-multiplying. Therefore, I specifically write here that I multiply with W on right hand side. Therefore, it becomes X transpose A transpose W less than equal to B transpose W. Say it is equation number 3. Now, the sign of inequality is preserved. Why so? Because W is non-negative from equation number 2. Therefore, sign of this inequality preserves. Now, we want C transpose X. Where is C in our picture? C is here in equation number 2. Therefore, we use equation number 2 that A transpose W is greater than equal to C. As we want C transpose, therefore I apply transpose on both sides. This becomes A transpose W whole transpose greater than equal to C transpose. Apply reversal law of transpose. This becomes W transpose. A transpose again transpose is quantity itself. Therefore, this is capital A. This becomes W transpose, A transpose transpose, A greater than equal to C transpose. Now we want X with C transpose. Therefore, again there is a concept of pre-multiply or post-multiply. I multiply with X on right hand side of above inequality. We get W transpose capital A into X greater than equal to C transpose X. This is say equation number 4. Again the sign preserve here because X is greater than equal to 0 from equation number 1. Now X transpose A transpose W is a scalar quantity. How this is a scalar quantity? We have X transpose A transpose W. Now we look how it is a scalar quantity. X is a n-dimensional vector. X is a n-dimensional vector. Therefore, X transpose is n-dimensional vector of the form 1 cross order of X is 1 cross n. Now A is matrix of order m cross n. This means A transpose is matrix of order n cross n. Therefore, A transpose is matrix of order n cross m. Now, what are W? W are dual variables, and we know the concept that the primal that dual variables are equal to the primal number of primal constraints. As number of primal constraints are m, therefore dual variables are also m. That is, W is m-dimensional vector. As W is m-dimensional vector, therefore order of W is m cross 1. Now multiply these two. This becomes n cross m, multiply with m cross 1, this becomes n cross 1. Now multiply again these two, this becomes 1 cross 1. Therefore, as this quantity's order is 1 cross 1, therefore this quantity is scalar quantity. Now the property of scalar quantity is that transpose of that quantity is quantity itself. Therefore, X transpose A transpose W whole transpose is equal to X transpose A transpose W. Apply reversal law of transpose on left hand side. This becomes W transpose, A transpose becomes A, and X transpose becomes X equal to X transpose A transpose W. Say it is equation number 5. Now combine equation number 3, 4 and 5. From equation number 4 we get C transpose X is less than equal to W transpose AX. C transpose X is less than equal to W transpose AX. From equation number 5, which is further equal to X transpose A transpose W. Therefore, this equal to X transpose A transpose W. And from equation number 3, we get this quantity is less than equal to B transpose W. Therefore, this quantity is less than equal to B transpose W. Combining these three, we get C transpose X is less than equal to B transpose W. That is, maximum value of our problem corresponding to feasible solution can't exceed minimum value of objective function corresponding to feasible solution. That is, C transpose X is less than equal to B transpose W. Now I am going to discuss corollary based on weak duality theorem. We have already discussed what is weak duality theorem. Now we discuss about corollary. Corollary is let X bar be feasible solution for the primal problem and W bar be feasible solution for the dual problem. Also, there is another one condition that these are those type of feasible solution corresponding to which objective function values are equal. That means C transpose X bar is equal to B transpose W bar. Then X bar is optimal solution to the primal problem and W bar is optimal solution to the dual problem. That is, if there are such feasible solution corresponding to which objective function values are equal, then that feasible solutions are also optimal solution to the problem. Now we go to proof of this corollary. Now we have to prove that X bar is optimal solution to the primal problem. We have to prove this. X bar is optimal solution to the primal problem. Say first we go to the definition of optimal solution. What is optimal solution? If optimal solution is that solution which gives maximum value to the objective function from all the feasible solutions. In our case, as primal is maximization problem, we say x bar is optimal solution of this problem if we prove that C transpose x is less than equal to C transpose x bar for every x in feasible solution. If we prove this, then we say that x bar is optimal solution to the primal problem. That means we say that x bar is optimal solution to the primal problem if in case of maximization value of objective function corresponding to this x bar is greater than equal to all values of objective function corresponding to all feasible solutions. We prove this. If we prove this, then we get the proof of our theory. Now come to this. Let x be any arbitrary feasible solution of the primal problem. We take x be any arbitrary feasible solution of the primal problem, and given w bar be the feasible solution of the dual problem. Now, since x is also a feasible solution and w bar is also feasible solution of dual problem, weak duality theorem apply here. What is weak duality theorem? What weak duality theorem states that corresponding to this type of feasible solutions, maximum value of objective function cannot exceed the minimum value of objective function. That is C transpose x, value of objective function corresponding to maximization problem is always less than value of objective function corresponding to minimization problem. That is C transpose x is always less than equal to V transpose W. Now it is given that V transpose W is equal to C transpose x bar. We apply it here. From this we get C transpose x is less than equal to C transpose x bar, where x is any arbitrary feasible solution. That means corresponding to any arbitrary feasible solution, value of objective function is always less than the value of objective function corresponding to x bar. Therefore, x bar is optimal solution to the primal problem. Similarly, we can prove that w bar is optimal solution to the dual problem. Now, the second corollary is that if primal problem is unbounded, then it is definite the dual problem is infeasible. Now we come to its proof. We prove this result with the help of contradiction. Let us suppose that dual problem has feasible solution, say W. Then by weak duality theorem we get C transpose x is less than equal to V transpose W. This means the maximum value of objective function in case of primal is always bounded above, as it get upper bound V transpose W. This means primal problem is bounded, but we have given primal problem is unbounded. Therefore, our supposition is wrong, and hence if primal problem is unbounded, then dual problem is infeasible. Now next is strong duality theorem. Consider the primal dual pair as we considered in weak duality theorem. The same primal dual pair is this. Now strong duality theorem states that if let x bar be an optimal solution to the primal problem, then there exists w bar which is optimal solution of the dual. Moreover, corresponding to these optimal solutions, value of objective functions are equal. This its second part says that if W star is optimal solution of dual, then there exists X star optimal solution to the primal, and also the value of objective function corresponding to these optimal solutions is equal. Change here. I am not going into proof of strong duality theorem, but you always remember the statement of strong duality theorem, which we further use in other concepts. Next theorem is dual of dual is primal problem. That if we take dual of primal and then we take dual of dual, then it comes primal again. Let's come to its proof. Let us consider primal problem as maximum z c transpose x subject to ax less than equal to b, x greater than equal to 0. Now its dual is, how to form its dual? I have already discussed. Its dual is minimize z star objective function. Right hand side of primal problem becomes cost coefficients of dual problem, and cost coefficients of primal problem becomes right hand side of dual problem. Therefore, this is the dual of this primal problem. Now I will take its dual again, that is dual of dual. Dual of dual, as now this is minimization problem, therefore its dual is maximization problem. Therefore it becomes maximize objective function. Now same thing, that its right hand side becomes cost coefficient of new problem. Therefore it becomes C transpose. Say here we take since z we already apply here, say this is z dash, we take z this z now as dual variable. Here z is dual variable. This becomes C transpose z subject to the condition. We take transpose of coefficient matrix. Here coefficient matrix is A transpose, therefore we take transpose of transpose. Then z is dual variables less than equal to, as variables are greater than equal to form, we can check from rule table. Therefore inequalities are of less than equal to type, and its right hand side comes from its cost coefficient. Cost coefficient is B transpose, therefore we take B transpose transpose. If we solve this, transpose of transpose becomes quantity itself, therefore this becomes AZ less than equal to B, and obviously as inequalities are greater than equal to 0 here, therefore all dual variables are greater than equal to 0. This is nothing but primal problem. Look at this and this. These both are similar. The difference is that here we use x as variables, here we use z as decision variable, and remaining problem is same. Therefore dual of dual is primal problem again. Now some important results are, if primal problem and dual problem both have feasible solutions, then both have optimal solutions. If primal or dual has unbounded solution, then the other problem, that is corresponding to primal there is dual, and corresponding to dual there is primal, then the other problem has infeasible solution or no feasible solution. And the third point is, if primal or dual has infeasible solution and the dual or primal has feasible solution, then the dual or primal has unbounded solution. This is the results based on all the duality theorem, that if primal and dual have feasible solution, then other have both have optimal solutions. If primal and dual has unbounded solution, then the other has no feasible solution. If primal and dual has infeasible solution or no feasible solution, and one information is more there that the other problem has feasible solution, then it is definite then that other problem has unbounded solution. Now we put all the information in the form of this table, that let here this side dual problem, here this side primal problem. Now we discuss one by one. If primal is feasible and dual has feasible solution, if primal has feasible solution and dual has feasible solution, then it implies that both have optimal solution. If primal has feasible solution and dual has infeasible solution, then it's definite that primal has unbounded solution. If Primal has infeasible solution and dual has feasible solution, then it is definite that dual has unbounded solution. This case is also possible. That is when both the primal and dual has infeasible solution. This case is also possible. That is primal and dual both could be infeasible solutions. This is the important table which is the result of all the duality theorems we put in the form of this table.
Friends, if you like this video, please subscribe our channel and press bell icon button to get notification of our new videos. Thank you friends. Keep watching our videos.